Hello everyone. This work presents a comparative analysis of three types of SRAM memory cells: 60, 70, and 80. We sincerely thank Dr. Shubhadeep Bhattacharjee for his valuable guidance through our project. We are also grateful to our classmates whose thoughtful suggestions inspired us to enhance the quality of our work. In this project, we perform a comparative analysis of three widely studied SRAM cells architecture: 60, 70, and 80. Our goal is to evaluate their trade-offs under identical simulation conditions and highlight which configuration offers the best balance for modern VLSI memory design. This research offers a comparative examination of 60, 70, and 80 SRAM cells developed using 65 nanometer CMOS technology, focusing on low power and high performance applications in embedded systems. As battery operated devices become more common, the design of energy efficient SRAM is essential for maintaining reliability, speed, and scalability within system-on-chip SoC architecture. The study also encompasses critical peripheral components, including pre-charge circuits, decoders, and sense amplifiers. Despite, despite the advancements in the VLSI that have significantly increased logic gate speeds, memory speed, particularly in SRAM, has not kept the pace, creating performance bottlenecks in high-speed systems as CMOS technology scales down. Conventional 60 SRAM faces challenges such as increased leakage, reduced reliability, and higher manufacturing complexity. This project addresses these limitations by exploring 60, 70, and 80 SRAM designs that aim enhance noise margins. Here is the structure of a 60 SRAM cell is mentioned, where cross-coupled inverters M1, M2, M3, and M4 store the data and access the transistors M5 and M6. Enable the read or write operations through bit lines when the word line is activated. Now, a key challenge is this design in the read or write conflict due to the shared data paths, which can disturb stored values. Now, can we work only with the bit line in SRAM instead of having the both bit line and bit line bar? So the answer is no. Both bit line and bit line bar are essential for differential sensing, and which can disturb the stored values. So essential for differential sensing to ensure stability and noise immunity. Here is the read operation of the 60 SRAM cell, wherein the pre-charged bit lines and the activated word lines facilitate the access transistors in transferring the stored data to the output while preserving its integrity. It's crucial to manage the voltage swing at node Q to avoid inadvertent bit flipping, that is 0 to 1 or 1 to 0, which may result in destructive read. This susceptibility underscores the necessity of for advanced SRAM architectures like the 80 cells that segregate the read path to bolster stability. Here is the circuit explains the right operation in the 60 SRAM cell, where the data is written by applying appropriate voltages to the bit lines and the enabling access transistors via the word line. The write process flips the stored value, that is Q is equals to 1 to 0, and after that stored value by overpowering the cross-coupled inverters, which is achieved through careful transistor sizing. So the key parameters like cell ratio and pull ratio are determine the effectiveness and the stability of the write operation. So this is over here, pull ratio and the effectiveness will be decided by the cell ratio. The 80 SRAM cell, which is using the 6T transistors, 4 in the inverter and 2 on the excess transistor side. So, and 2 additional on the to create a separate read path, ensuring the internal nodes remain undisturbed during the read operations. This decoupling of the read and the write paths improves stability and removes the sizing conflicts between the read complexity and reduced bit density compared to the conventional 60 SRAM. The 70 SRAM cell retains data during the hold operation using two cross-coupled inverters as long as power is supplied. All excess transistors remain off and no switching occurs, minimizing the power consumption. For example, if the stored value Q is equals to Q equal to 0, that if the stored value is 0, Q remains at VDD and Q bar stays at 0 volt, maintaining the state through feedback. Here is the 70 SRM read operation where an extra NMOS transistor, that is the N5 basically creates a separate read path, isolating it from the node Q and Q bar during a read. If the stored value is 0, the bit line is discharging through N4 and N5 directly through N4 and N5. If bit line was VDD, it is basically discharging from here. And if the value is 1, so the if the value is 1, the MOSFET N4 will switch off and there will be no path to discharge, making so the bit line remains high due to no discharge path. So this isolation makes the read operation non-destructive and enhancing the stability compared to the conventional 60 SRAM. The 70 SRAM cell performance in the write operation using a single bit line and the single word line. Now with transistor N3 allows the data on the bit line to override the cell's store value over here at Q. So Q can be 1 or 0 is achieved by setting the bit line at VDD or 0 respectively while the read path remains inactive. So it will be managed by MOSFET N3 with respect to word line. Now here comes is the 80 SRAM write operation, which functions the same way as in a 60 SRAM cell using the excess transistors M3 and M4, then now controlled by the write word line. So M3 and M4 excess transistors are connected with respect to the write word line. To write the data, appropriate voltages are applied to the bit line and the bit line bar, and enabling the write word line allows the desired logic value to be forced into the node Q. So the extra two transistor you see, M5 and M6 used for read isolation remains inactive during the write, ensuring the write path remains efficient and unaffected. Now here we see 80 SM read operation where a separate read path using the transistors M5 and M6 allows the data to be read without the disturbance or the disturbing the nodes at Q and Q bar. If Q is equals to 0, definitely Q bar equals to 1 and Q bar is connected over at the gate of MOSFET M6 will make it on, and there will be, so both M5 and M6 will get on and creating a discharge path with that pulls the read bit line low to indicate a stored 0. So Q is stored 0. If Q is equals to 1, Q bar will be equal to 0 and 0 will come here. So M6 will be off, and but the right bit line stays high. The right bit line stays high. That right bit line which stayed high, now creating a discharge path in this M6 remains off and the right bit line stays high. This indicates the stored 1. This non-destructive read mechanism enhances the stability and reliability compared to the conventional 60 SRAM designs. This here presents the method used to calculate the noise margin of the SRAM cells through the butterfly curve approach. Demonstrate of a 60 SRAM. Voltage transfer characteristic VTC are exported from the cadence as a .svm file. Now which is processed in MATLAB to generate a q.mat and qb.mat files. Two files are made by this .svm file which was there in Cadence. Now after containing the voltage data of the node Q and Q bar. Those two files will save. These files are then used to plot the butterfly curve in the MATLAB, where the static noise margin is computed by fitting the largest possible square between the mirrored curves. Here is the slide shows the 60 SRAM cell schematic with the cross-coupled inverters for data storage and access transistors controlled by the word line for read or write operations. The accompanying test bench includes the input drivers and an encapsulated SRAM block to simulate real operating conditions like read, write, and hold together. These setups validate the functional behavior of the SRAM cell under different scenarios. Here we see two peripheral circuits used in the SRAM design, the pre-charge circuit and the read-write multiplexer. The pre-charge circuit uses PMOS transistors to set the both bitline and bitline bar to VDD before a read, enabling the accurate differential sensing. And this third benefit of using this PMOS will manage that proper equality comes over when the pre-charge is happening. That both lines bitline and bitline bar will get at the VDD. This MOSFET balances it. Now the read-write mux uses the logic gates to select whether the data is read from or written from the memory cell based on the control signal. So we have taken an inverter where due to this opposite polarity, one bit can be taken as a read and another for a write with this operation. So it is done via mux. Here we see the complete simulation of a 60 SRAM cell using the read and write cycle, verifying its correct behavior through the schematic setup and the transient output. The top level schematic in figure 5 we see shows that how the SRAM cell is integrated with the bit lines. Then we are having a word lines, then we are having voltage sources, then we are having sense amplifiers, and then we have to simulate one full read and write. Now to simulate one full read and write operation, so the output waveform 6 captures the transition on the word line where the word line gets turned on. There is a word line over here at blue, so it basically turns on. So the word length, which is basically turning on at 0.5 nanoseconds, enable the access transistors M5 and M6. Bitline bar, which is here, basically drops at to 0 volt just before 0.5 nanoseconds. So this is the 0.5 mark. Over before that, it basically drops actually, and used to write a logic 1 into the cell. The Q stored, which is a stored node, which is a fourth rise. If we see here, this one basically starts from 0 to 1.2 volt between 0.5 nanosecond, between the 0.5 nanosecond and to 1.1 nanosecond. Successfully stores the logic 1. And complementary of that is nothing but Q bar is which will basically falls from 0.5 volt to 0 volt into same interval, and complements the Q indicating logic 0. So it is basically starting at the start is from 0.5 nanosecond when word line goes high, and is actually at 1.1 nanosecond. So at 1.1 nanosecond, start with 0.5 and 1.1. So the right time for this is nothing but 0.6 nanoseconds. So, and bitline will be high throughout. This is the bitline signal. This will be high throughout. This schematic shows the 70 SRAM cell that uses the cross-coupled inverters M1, M2, M3, M4 as shown to store the data, and the single access transistor M6 for writing via word line. A separate read path is formed by the transistor M5 and M7 controlled by the read line, and enables non-destructive read operations without the disturbing the stored data. This design improves read stability and reliability compared to the traditional 60 SRAM, especially in the advanced CMOS technologies. These schematic shows the complete test bench used in the verify of the 70 SRAM cell that basically includes the write hold read operations. It consists of one precharge block, one read write mux, a sense amplifier, all controlled through the input signals like uh, write word line, read word line, and data lines. The bottom part focuses on individual cell level verification as we are doing it for 80-bit cell. Um, so to observe the signal behavior at the transistor level during the simulation. This plot shows the butterfly curve for 70 SRAM cell generated by plotting the voltage transfer characteristics for Q versus Q bar and Q bar versus Q of its cross-coupled inverters. The static noise margin is determined by the fitting the largest square between the mirrored curves, indicating the cell's resistance to noise. This schematic shows 80 SRAM cell, which basically includes the 60 core cell SRAM cell for storage and a separate 2T read stack for non-destructive read operations. The write operation uses access transistors M5 and M6. These are access transistor M5 M6, which is basically having write word line, and while the read path formed by M7 and M8 are controlled by the read word line, and safely reads data without disturbing the internal nodes. This separation improves the read stability, sensing margin, and enable better timing flexibility compared to the conventional 60 RAM. This plot presents the butterfly curve used to calculate the static noise margin for the 80 SRAM cell, derived by plotting Q versus Q bar and vice versa from its voltage transfer characteristics. Now coming to this waveform, one is the precharge phase. We say the precharge, that is the first signal, is getting high, and the bit line and bit line bar basically gets precharged. Once the precharge is basically getting high, so we can see that bit line and bit line bar basically gets high. They get precharged. Now, the first one, the pre-charge phase. Coming to the second phase, that is called as the write operation. In write operation, we take the select signal that is asserted, directing the data. Now, there is data in basically, which is basically and data in B, data in and data in bar, both basically are complementary to each other. Now the right word line we see here, this is the right word line. So right word line basically goes high, and the data gets returned to Q and Q bar. So we will see corresponding changes in the Q and Q bar waveforms. Coming to the read operation, after a delay, the read word line is asserted. So we have a read word line basically that is asserted, and based on that, the bit line remains stable. So the bit line remains stable while the read bit line discharges depending on the value of the Q, and the Q and Q bar remains unchanged, confirming non-destructive read. We can see here they are non-destructive read, and that's how that's how this is done. Now this slide shows a butterfly curve used to calculate the static noise margin of a 60 SRAM cell by plotting Q versus Q bar and Q bar versus Q. So the curve intersects to form the region where the largest possible square fits, and between them and yielding an SNM, static noise margin of that we'll see, and this value reflects the cell's ability to resist the noise induced bit flips, indicating the moderate read stability. So here we demonstrate the MATLAB based calculation of the static noise margin of a 60 SRAM cell. From previous uh, plot, we got to know the butterfly curve. Now this butterfly curve is basically transferred into the file in Cadence called as .svm file. That .svm file is now is taken out and extracted in terms of two files. One is Q and Q bar. Those Q and Q bar is having an extension to be .mat, in because we are basically calculating the static noise margin in MATLAB. So that's what our methodology is. So over here we basically .svm file is converted into q.mat and qbar.mat. These two files are basically loaded over here in the MATLAB. So read q. So we are taking an example of a 60 SRAM cell where load read q 60.mat and load read qb 60.mat are there. And now basically after that we will basically extract these files into this way. So these are two matrices. One is VTC1 and VTC2. Over here, data1 dot data and data2 dot data. So one will have Q and one will have Q bar. Those two matrices will get the values. After that, we will find out the read noise margin of 60 by having noise margin high and noise margin low. So the noise margin high, we get it to be 0.223 volts, that is 223 millivolts, like this. So here we got the noise margin of margin 0.223 volts for 60 SRAM cell. Now noise margin summary, if we take, so in previous slide we got 6 transistor, 6 T SRAM, a noise margin to be 223 millivolt. Now if we come across the 1780, the same, we also done the same noise margin process in the same way. So for 70 SRAM we get noise margin to be around 280 millivolt, and for 80 SRAM we get the noise margin around 350 millivolt. So as we are increasing transistor to transistor, so each added transistor clearly improves the static noise margin. One previous was 223 millivolts, added one transistor we get 70 is having 280 millivolts, and adding one more transistor 80 SRAM we get 350 millivolts. So each and every transistor clearly improves the static noise margin. Here we outline the future scope of the SRAM in the emerging computing technologies. SRAM is increasingly vital in the AI accelerators, in memory computing systems, and neuromorphic hardware due to its low latency and energy efficiency. These applications highlights SRAM potential to overcome the traditional memory bottlenecks and support advanced brain-inspired architectures. These are the references that supported the technical foundation of the SRAM design project. It includes prior research on 80 charge sharing techniques, energy efficient 60 SRAM for multimedia, and SNM enhanced SRAM designed for the scaled CMOS. These works guided the analysis for noise margin across 60, 70, and 80 SRAM architectures. Thank you for listening and for all the guidance we received. We welcome any questions or suggestions you may have. Thank you.